Hey everyone, welcome back to another AMC problem solving strategy video. My name is Sol, and today we're going to be going over complex numbers. Now, this isn't really a topic that appears on the AMC 10, although it could indirectly. It's not actually, the test isn't actually going to ask you a question about these, but it does show up at least once or twice on the AMC 12, and again once or twice on the AME. So I thought that this video might be really useful for those of you guys who are going into those tests. So first of all, what is a complex number? Well, a complex number, z, can be defined as follows: some a plus bi, where a and b are some real numbers, and I is equal to the square root of -1. So this is pretty simple. I mean, if you guys have worked, or if you guys have gone through Algebra 2, you guys should be pretty familiar with this concept of I. So just some basic notation regarding complex numbers. First we have this, z bar, or z conjugate. And basically if z was a plus bi, then z bar would be a minus bi, the complex conjugate of z. And then we also have this, the absolute value of z, which is equal to the square root of a squared plus b squared. And you know, we've defined absolute value, at least in a one-dimensional space, or a one-dimensional space, as just you know, the distance from 0. So if we think about what this would look like on, say, a complex plane, let's say I have a point like here, and let's say this is z, then we can think about the distance as, say, we can think about the distance as just, or the distance from the origin. We can take it very literally and just say that, well, if this is b and this is a, then this is going to be the square root of a squared plus b squared by Pythagorean theorem. So that's how that works. Now, this is just some basic stuff, and if you guys notice that this is also a property, just a basic one. But there is another way to define complex numbers, and that is through cosine plus I sine. So z can, any complex number z can also be expressed like this: cosine theta plus r I sine theta. Or people like to shorten the cosine theta plus I sine theta to just name it cis, or cis theta. So yeah, it's like this. So what does this mean? Well, I mean, if we think about it, right, we have every complex number, right, is some angle from the horizontal here, some angle theta from the horizontal, and it is some distance away from the origin. And that's essentially where this definition of complex numbers comes from. Or yeah. So one interesting thing that can be proved through Taylor series and a bit of calculus, if you guys are there, is that this cosine plus I sine theta is also equal to this. Now, you guys might be familiar with this e to the theta I, especially if you've seen this equation before. E to the pi I plus 1 is equal to 0, which implies that e to the pi I is equal to -1. So let's just think about this for a bit. So the r in front of this term right here is technically just, well, it's technically just 1, right? So it's 1 times this e to the pi I. And the angle that this is tilted at is pi radians, or 180 degrees. So we go all the way over here to this side. We look at what real number this is, and this would be -1, which is how this result comes to be. So yeah, this has some pretty interesting applications, especially when solving for roots of polynomials. You guys might be familiar with this as well. as they're called the roots of unity. So yeah, let's get into that. Alright, so before we talk about the roots of unity, we need to talk about something called, or to find these roots of unity, we need to talk about something called DeMoirs Theorem. If I could please write an E. Sorry, my tablet has not been the best, but DeMoirs Theorem, I think that's how you spell it. So, if you guys have been through calculus, or pre-calculus, my bad, then you guys have probably already encountered this theorem. However, I know, especially last year, because the semester got cut off and cut in half, you guys probably didn't get to this, or maybe briefly went over it. So, what does DeMoirs theorem say? Well, if we have a some polynomial like this, well, I think an obvious answer for this, an obvious solution for z is r, right? But there are actually n-1 other solutions to this polynomial. And, well, that is pretty obvious because of the fundamental theorem of algebra. But these roots, these n-1 other roots, are all complex. So, how can we find them? Well, DeMoirs theorem states that every other integer takes the form of this. So I think this is 2 pi I k over n, where k is some integer, and the thing about this is, because we're talking about kind of this cyclic nature on the complex plane, like I said, so let's kind of draw this line here, draw another one here. This will be the real line, and this will be the imaginary one. If you think about it, there are only a few values of k that we really need to examine, mainly because, well, you know, this is going to be some theta, right? 2 pi k over n. So if we go around enough, or if we rotate around enough, we're going to end up back where we started. So you only actually have to test n values of k, and that would be from 0 to probably n-1. But don't memorize that. You guys can probably figure that out on your own. Like if, I don't know, if n happened to be 4, then this would be like r times, let's see here, pi I k over n 2. And so if we plug in 0, then we'll get this point right here, such that this is a distance r away. If we plug in 1, then we'll get a point here, and this is also r away. If we plug in 3, or 2, my bad, then we'll get a point here. This is also r. And if we plug in 3, then we'll get this, which is also r. And if we plug in 4, we'll end up right back here. So yeah, like I said, there are only a few values, n values, that you have to test for k. So that is essentially DeMoirs theorem, and this also leads to the roots of unity, mainly because, well, these are the roots of unity. Although usually the roots of unity have a magnitude of just 1, so this would be a 1 instead of r, some general r. But it should be noted that this is basically just how you find the solutions to these kinds of polynomials. Alright, so now that we have that down, hopefully you guys have gotten a pretty good understanding of how this works. Let's try to solve a problem involving DeMoirs theorem. Alright, so now that we've gone over DeMoirs theorem, we're now going to go over this problem. I believe it is number 17 from the 2017 AMC 12A. So it's a problem that's pretty late into the test, but I assure you that once you guys know DeMoirs theorem, this is essentially just a basic exercise. So it says that there are 24 different complex numbers z such that z to the 24th is equal to 1. For how many of these is z to the 6th a real number? Okay, so like I said before, we have some equation like this, right? And we can rewrite this just so that we're a little more comfortable using the formula, or the form of DeMoirs theorem. We can write it like this. So, like I said, the solutions would end up becoming something like z equals, well, r is 1 in this case, so it would just be e to the 2 pi ki over 24, because n is 24. So we can just simplify this a bit to make it this, e to the pi ki over 12. And we just have to test, like I said, we just have to test a few values of k. Well, I know that I want to test 0, I want to test 1, and if we think about it, if we plug in 24 for k, then this will just become e to the 2 pi I, which is the same thing as e to the 0, so I'm only going to test up to 23 for the integers. These are all the values, all 24 values that k could take on. Otherwise, the other roots will not be unique. So we found all 24 roots just like that, and we need to find for how many of these is z to the 6th a real number. Okay, so let's just write z to the 6th, knowing that this is z right here, this would be e to the pi ki over 12 times 6. This goes away and this becomes 1/2. So this is just e to the pi ki over 2. Okay, so let's think about what this means, right? Let's think about what this means. So where is my line tool? Hold on. There we go. Alright, so if we draw our complex plane here, where these are the imaginaries, of course, and these are the real numbers, we want to think about what this would look like, right? So because we want z to the 6 to be a real number, we want it to lie somewhere on this real axis, right? So if we plug in 0, we find that it lies there. If we plug in 1, it goes here. If we plug in 2, it goes here. If we plug in 3, it goes here. So we've in just that amount of time, we've basically found that every even value of k will result in something on the real number line, which is what we want, right? And an odd value of k will result in an imaginary number, something that we don't want, something that the problem doesn't want, as shown here. So since we know that it's divided into evens and odds, we know that there are 24 elements in here, and half of them are even, half of them are odd, so we just divide by 2, and you get there are 12 values of k, and therefore 12 zeros of this polynomial that such that z to the 6th is a real number. Our answer is D, and we are done.